Hello, welcome to my video on data structures. In this video, we will discuss a different hash collision handling approach called alternative probing. Recall that hash collision happens when two different records having the same hash value and compete for the same location in the hash table. One way to address the issue is separate chaining, where we append the colliding records all together into a single linked list. There are two limitations for the separate chaining approach. First, it's relatively complicated to implement, as it involves two different data structures, vector and linked list. Second, it is memory inefficient and requires to store many pointers for the linked list. On the other hand, the alternative probing approach, or probing for short, tries to address these issues. Instead of appending the colliding records altogether into a single linked list, the probing approach tries to assign different locations for the colliding records by using different hash functions. To be more precise, recall how we handle collision with separate chaining. Here, we first have a record R that comes in. We apply the hash function f to R and get a resulting hash value of 2. In this case, we store the record R into the location T2. We do the same for the second record R' and obtain the same hash value 2. Now, a collision happens, as two different records, R and R' have the same hash value of 2. With separate chaining, we simply append the record R' to the end of R and form a linked list. Now, let's see what would happen with alternative probing. Still, we have R comes in first and being stored at T2, followed by R' that causes a collision. Instead of directly appending R' to R, we will find a different hash function f' for R'. The new hash function f' changes the resulting hash value from 2 to 7, and we shall store R' in T7. It is easy to see that with alternative probing, we can get rid of the linked list and the hash table becomes a vector. It also means that the data structure will be more memory efficient as we get rid of the pointers for the linked list. On the other hand, probing can be less computational efficient. This is because an insertion can trigger a series of failed probings, which require us to compute many different hash functions. For example, applying a hash function f1 to the record R results in hash value v1, but we can find that tv1 is occupied. We then try a different hash function f2 and get a hash value v2, but tv2 is also occupied, and so on and so forth. As a result, we have no idea how many probings we need to perform before settling the new record into an empty location. Now, after discussing the basic idea of alternative probing, we have two practical issues remain. First, how do we choose the set of hash functions when we do not have a bound on how many we need? Second, can we always find an empty location to accommodate a new record? Let's first discuss how to choose the set of hash functions. A simple solution to generate a series of hash functions is to take the number of failed probings as a parameter in the function. For example, consider the hash function fxi shown here, where x is the key and I is the number of failed probings. Fx can be whatever hash function that we intend to apply initially, and f'I is a function that depends on I. Let's consider the simplest case, where we take f'I equals to I, fx equals to x, and we assume the hash table size m equals to 10. For the key 89, the first time we compute its hash value corresponds to 0 probing failure and I equal to 0, and the resulted hash value would be 9. If location 9 is occupied, we will have the first probing failure and we'll compute its hash function for the second time. The second time we compute its hash value does correspond to 1 probing failure and I equals to 1, and the resulted hash value will be 0. We can further see that the third hash value will be 1 and the fourth hash value will be 2, and so on and so forth. Therefore, with linear probing, we are essentially searching the hash table locations consecutively and trying to find the next available location. Let's see what would happen with linear probing. Consider the example shown here. The first insertion is 89, and we'll put that into T9. The second insertion is 18, and we'll put that into T8. The third insertion is 49. We'll first try to put it into T9 but failed. With linear probing, we'll try T0 and successfully put it into T0. Now, the insertion of 58. We begin with T8, failed, then T9, failed, then T0, failed. Finally, we'll put it into T1. Similarly, for the insertion of 69, we have to try T9, T0, and T1 before settling it down at T2. If you look at the resulted table, you will realize that all records are locally cluttered, and any initial insertion into the clutter must go a long way before finding an empty location. Luckily, since we are essentially searching for every available location throughout the entire table, we can always accommodate a new record as long as the table is not full. To address the issue, we can use quadratic probing, where we simply take f prime I equals to I squared. For the key 89, we can see that its first hash value will be 9, the second will be 0, the third will be 3, and the fourth will be 8, and so on and so forth. You can see that with quadratic probing, the step size for the search of the next available location is increased quadratically with the number of probing failures. Intuitively, quadratic probing allows us to create a less cluttered distribution of the records and also enables us to jump out of the cluttering faster if there are any. Now, let's rework the previous example with quadratic probing. The first two insertions of 89 and 18 are successful for the first place. To insert 49, the first attempt at T9 is failed, and the second attempt thus has a step size of 1 square, which is 1. We therefore try T0 and are successful. To insert 58, the first attempt at T8 failed, the second attempt with a step size 1 square at T9 also failed, and the third attempt with a step size 2 square at T2 is successful. Similarly, for 69, the first attempt at T9 failed, the second attempt with a step size 1 square at T0 also failed, but the third attempt with a step size 2 square at T3 is successful. Indeed, by comparing the resulted table with the one generated with linear probing, we can see that it is less cluttered. However, a drawback is that we do not know whether we can always find a location to store a new record with quadratic probing, since we are no longer probing every single location in the table. Luckily, we have a theorem to address our concern. The theorem says that if the table size is prime and it is at least half empty, Then we can always find a location for a new record. The two conditions can be ensured with the table doubling strategy we introduced before. The proof of this theorem will be introduced in the next video. In summary, we have discussed the alternative probing approach for handling hash table collision. Comparing to separate chaining, alternative probing uses less memory but more time. For the design of hash function series, we recommend using quadratic probing with table doubling. Thanks for watching and see you next time.